Every integrand we have met so far has been a scalar, a height, a density, a temperature, a probability per unit volume. Today, we change the rules in two ways at once. The integrand will be a vector field, a function that attaches an arrow to every point in space, not a single number. And the domain over which we integrate will not be an interval, a planar region, or a solid. It will be a one-dimensional object embedded in a higher dimensional space, a curve. The result is the line integral over c of f dot dr, which evaluates to a single number, the integral from a to b of f of r of t, dotted with r prime of t dt once you parametrize the curve. Its physical meaning is work, force dotted with displacement, summed along the path. The same notion you met in introductory mechanics, now upgraded from a single constant force times a single straight displacement to a varying force along a curved path. We will work 3 concrete examples on this slide deck, see why the same curve can give wildly different answers under different fields, and discover the punchline that line integrals can depend on the entire path between two endpoints, not just the endpoints themselves. That last observation is the doorway into conservative fields and the fundamental theorem of line integrals next episode, and it is the gateway to Green's, Stokes, and the divergence theorem after that. Definition first. A vector field on a subset D of n-dimensional space is a function f from D into n-dimensional space. The key feature, the input and output dimensions match. In one dimension, that's a real valued function of one variable. Boring. In 2 dimensions, f of x, y equals the vector p of x, y, q of x, y, a pair of scalar fields packaged together. We visualize it by drawing, at every point x, y, a small arrow whose tail is at x, y, and whose tip is at x, y plus f of x, y. Examples everywhere in physics. Near Earth surface gravity is the vector 0, negative g d d d d. Uniform downward arrows. The radial field, the vector xy, has arrows pointing out from the origin, growing in length. The rotational field, the vector negative yx, has arrows tangent to circles around the origin, a swirl. Electric fields, fluid velocity, magnetic fields, force fields, vector fields are the language of vector calculus. Here is the geometric picture. The blue arrows are samples of a vector field on a grid, in this case the rotational field, the vector negative yx, suggesting a counterclockwise swirl. The red curve C threads through that field from lower left to upper right. At each point on the curve, 2 arrows meet, the field f, evaluated at that point, black, and the tangent vector r prime of t to the curve orange. The line integral measures the alignment between them, integrated over the trip. If the field consistently points along the curve, the integral is large and positive. If it points against the curve, negative. If it is perpendicular, 0 contribution. The result is a single number that captures how much the field pushes a particle as it travels along C. This is the picture you should hold in your head every time you compute a line integral, a curve in the wild, passing through a field of arrows, with every infinitesimal step harvesting its contribution as a dot product, all summed up by an integral. Before we integrate, we have to give the curve C a parametric description. Geometrically, a curve is just a set of points. Analytically, we need a function that traces it out. A parametrization is a continuous map R from an interval a to b into n-dimensional space whose image is C. In 2 dimensions, r of t equals the vector x of t, y of t. At time t, you are at the point x of t, y of t. The tangent vector is the component-wise derivative. R prime of t equals the vector x prime of t, y prime of t, pointing in the direction of motion. The differential, dr equals r prime of t t t, packages a tiny step along the curve. Examples to keep in mind. The parabola y equals x squared from the origin to 1, 1, parametrizes naturally as x equals t, y equals t squared, with t in 0 to 1. The unit circle parametrizes as the vector cosine t, sine t, for t in 0 to 2 pi, traversed counterclockwise once. Pick a good parametrization and the computation writes itself. Before the main event, a quick stop. There is a second species of line integral, the scalar one. Given a scalar field f defined on the curve, the integral over c of f, ds, weights f by arc length. The arc length element ds is the magnitude of the tangent vector times dt. It measures the tiny distance you cover in time dt. Geometrically, chop the curve into tiny pieces, multiply f at a sample by the length of the piece. Sum, take the limit. 2 readings. With f identically 1, you recover the arc length of c. With f a linear mass density, you get the mass of a wire shaped like c. The scalar line integral does not care about orientation. Traversing c forward or backward gives the same answer, because the magnitude of r prime of t is always positive. The vector line integral, our main topic, will not be so forgiving. Quit mental model. The scalar integral integrates a number along a curve. The vector integral integrates an arrow along a curve via dot product with the direction of travel. 2 different animals sharing the same notation, the integral over c. Here is the main definition. Let f be a continuous vector field on a region containing a smooth curve, C, parametrized by r from a to b into n-dimensional space. The line integral of f along C is the integral from a to b of f, evaluated at r of t, dotted with the tangent r' of t with respect to t. In coordinates, if f is the vector p, q, and r is the vector x, y, the integrand becomes p times x' of t plus q times y' of t, often written more compactly as p dx plus q dy. Two crucial structural facts. The result does not depend on which parametrization you chose for C. Two different speed profiles along the same oriented curve give the same answer. But it does depend on orientation, reverse the direction of travel, and the integral changes sign, because r' of t flips. So an oriented curve, not just a curve, is the proper input. Whenever you see the line integral over C of f dot dr, mentally append the phrase in the direction specified to the symbol C. The p dx plus q dy form is exactly the same object. Dx and dy are shorthand for the components of dr. Use whichever notation makes the computation cleanest in context. Where did this peculiar definition come from? Physics. In high school mechanics, the work done by a constant force, F over a straight displacement d, is the dot product F dot d, which equals the magnitude of F times the magnitude of d times cosine theta, where theta is the angle between them. Push perpendicular to the motion and you do no work. Push along the motion and you do maximal work. Now generalize. The force varies from point to point, a vector field, and the path is curved, a parametrized curve. Locally, over a tiny segment dr, the force is nearly constant. The infinitesimal work is F dot dr. Add all the infinitesimal contributions along the curve and you get the line integral over C of f dot dr. That is exactly the definition we just wrote down. The line integral of a vector field is, in physical language, the work done by that field on a particle traversing the curve. Same definition every time, pointwise dot product between field and tangent, integrated along the parameter. Everything else, the choice of curve, the choice of parametrization, the choice of field, is bookkeeping. Here is the picture that makes the definition concrete. The red curve is C. I have placed 5 sample points along it. At each sample, 2 arrows, the orange one, dr, lies along the curve, a tiny step in the direction of motion. The blue one, f, is the vector field evaluated at that point. The contribution of this sample to the line integral is the dot product f dot dr, the projection of the field onto the direction of motion, times the length of the step. Sum over all samples, shrink the step size, take the limit. That limit is the line integral. If f and dr tend to point in the same direction, the integral is large and positive. If opposite, large and negative. If mostly perpendicular, small. In the limit, the finite sum of dot products becomes the line integral over C of f dot dr. The Riemann sum mindset transfers verbatim from one variable calculus, only the integrand changed, from a scalar height to a scalar dot product. First worked example, designed to drill the mechanics. Compute the line integral over C of y dx plus x dy, where C is the parabola y equals x squared from the origin to 1, 1. Step 1. Parametrize. The cleanest parametrization uses x itself as the parameter, x equals t, y equals t squared, with t running from 0 to 1. Step 2. Compute the differentials. dx equals dt, dy equals 2t, dt. Step 3. Substitute into the integrand. Y dx plus x dy equals t squared times dt, plus ttt dt, which is t squared plus 2t squared, dt equals 3t squared dt. Step 4. Integrate. The integral from 0 to 1 of 3t squared dt equals t cubed evaluated from 0 to 1 equals 1. Done. Read it as the line integral over C of f dot dr, with f the vector y, x if you prefer. The two notations describe the same object, and the substitution recipe is identical. Second worked example, designed to make geometry visible. The vector field is f of xy equals the vector xy, the radial field, arrows pointing directly outward from the origin. The curve is the unit circle, parametrized counter, clockwise as r of t equals the vector cosine t, sine t for t from 0 to 2 pi. Substitute the parametrization into the field, f of r of t equals the vector cosine t, sine t, the same vector as r of t itself because f is the identity radially. Compute the tangent, r' of t equals the vector negative sine t, cosine t. Now the dot product, cosine t times negative sine t plus sine t times cosine t equals negative sine t cosine t cosine t cosine t equals 0, identically 0 for every t. So the integral is 0. Geometrically, at every point on the circle, the radial field points outward while the motion is tangent, perpendicular to outward. Push perpendicular to motion, do no work. The particle goes all the way around the circle and the field has done exactly nothing. Third example, same curve, different field, dramatically different answer. The field is now f of xy equals the vector negative y, xt. The rotational field, arrows tangent to circles around the origin, swirling counterclockwise. The curve is still the unit circle, parametrized the same way. Substitute f of r of t equals the vector negative sine t, cosine t. Tangent, r prime of t equals the vector negative sine t, cosine t. Notice something, f of r of t equals r prime of t exactly, the field, on this curve, points in the same direction as the motion with the same magnitude. The dot product is the squared length sine squared t plus cosine squared t equals 1 identically. The integral is the integral from 0 to 2 pi of 1 dt equals 2 pi. Same curve as the radial example, different field, answer 2 pi instead of 0. The rotational field aligns with the motion everywhere, so it does maximal work. The radial field is perpendicular to the motion everywhere, so it does no work. Two fields, one curve, two stories. The line integral is sensitive to the relationship between the field and the path. It returns a number that measures how cooperatively the two interact. A closed curve is one whose start and endpoints coincide. A loop. The unit circle is a closed curve. We traversed it from t equals 0 to t equals 2 pi and ended up back where we started. The standard notation for a line integral around a closed loop is the closed line integral, written with a circle in the integral sign. Now look at what we have. The radial field around the unit circle, the closed line integral over c, is 0. The rotational field around the same circle, the closed line integral over c, is 2 pi. Two fields, one loop, completely different answers. This is the punchline. Some fields have the property that their integral around every closed loop is 0. Those are the conservative fields, and they come from gradients of scalar functions. F equals the gradient of f, which is why the loop integral collapses to f at the end minus f at the start, 0, whenever start equals end. Other fields, like our rotational one, are not conservative. They carry circulation, and the loop integral detects it. This is the topic of the next episode and the gateway to Green's, Stokes, and the divergence theorem. Step back from closed loops to two general endpoints A and B, joined by two different paths, C1 and C2. In general, the line integrals of a vector field along C1 and along C2 are different numbers even though the endpoints agree. The integral cares about the path, not just the endpoints. This is a feature, not a bug. In physics, it is exactly what distinguishes friction, path-dependent. The longer the path, the more energy loss from gravity. Path-independent, only the height difference matters. And it is logically equivalent to the closed loop story. The integral over C1 being different from the integral over C2 between the same endpoints is the same as the closed line integral being non-zero on the loop, C1 followed by C2 backward. Fields for which all paths between the same endpoints give the same answer are called path-independent, or equivalently conservative. They are the well-behaved minority, and the next episode is entirely devoted to them. Compressed recipe. Step 1. Parametrize the curve, choosing an r of t on some interval a to b that matches the orientation you want. Step 2. Compute the component-wise derivative r prime of t. Step 3. Substitute the parametric expressions into the components of the field. This turns f into an explicit vector-valued function of t alone. Step 4. Take the dot product of the field with the tangent, a scalar function of t. Step 5. Integrate that scalar from a to b by ordinary single-variable calculus. Cheap sanity checks. Units should be force times length, which is energy. Reversing the orientation must split the sign. If you can see geometrically that f is perpendicular to the curve everywhere, the integral is 0 before you compute anything. These three checks catch most arithmetic disasters. Recap. A vector field f from n-dimensional space to n-dimensional space assigns an arrow to every point. Parametrize a curve, c by r of t on a to b, with tangent r prime of t. The scalar line integral over c of f, ds, weights f by arc length and gives, for f identically 1, the length of the curve. The vector line integral over c of f dot dr is the integral of f dotted with the tangent, physically, the work done by f on a particle traversing c. 3 worked examples. The line integral over c of y dx plus x dy along the parabola from the origin to 1, 1, came out to 1. The radial field on the unit circle gave 0 perpendicular to motion. The rotational field on the same circle gave 2 pi aligned with motion. The closing observation: line integrals can depend on the path, not just the endpoints, a fact that classifies fields into the conservative, path-independent ones and everyone else. That's vector fields and line integrals. The integrand is now a vector field. The domain is a parametrized curve. The result is a single number, computed by dotting the field with the tangent and integrating with respect to the parameter. Physically, work done by a force along a path. If this helped, like, subscribe, and try today's challenge. Compute the line integral over c of f dot dr for f the vector 2xy x squared along any smooth curve from the origin to 1, 2. Try two different paths, a straight line and the broken path going right then up, and see what you get. The hint is that f is the gradient of x squared y, which means the line integral over c of f dot dr equals x squared y evaluated from 0, 0 to 1, 2, which is 2 no matter which path you choose. That is the fundamental theorem of line integrals, and it is exactly the topic of the next episode. See you there. A vector field on r to the n is a function f, r to the n to r to the n, an arrow attached to every point. Given a curve, c parametrized by r of t on a dd tie, the line integral of f along c is in tcf dot doctor equals in ta to the bfr of t dot r prime of t dt, the dot product of the field with the tangent, integrated. Its physical meaning is work, force times displacement, accumulated. Scalar line integrals in tcf ds instead, weight f by arc length, ds equals r prime of t dtd. The three worked examples gave 1, 0, and 2 pi respectively. The last two were over the same curve with different fields, and the third was non-zero over a closed loop. Proof that line integrals can detect the rotational structure of a field. They can also depend on the path between two endpoints, not just the endpoints themselves. Next episode, when does path dependence vanish? The answer is the theory of conservative fields and the fundamental theorem of line integrals, the multivariable analog of the FTC. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.